Good morning and welcome to Physics 4C. Today is March 24th. Today we're going to cover a couple of problems from the previous chapter, from chapter 18 that is. And then we're going to introduce chapter 19. And so we're getting really into the serious stuff for this class. I know we did problem 67 from this class, from chapter 18. So, and I promised that we're going to do problem 68. So we're going to do problem 68. Problem 78, we're probably going to touch upon it. We're not going to go into details on how to do that because it's just numerical data. We're going to talk about it to do that. Problem 73 and 76 are interesting. And we'll talk briefly about them, and then we're going to jump into chapter 19. So this is basically, in a nutshell, what I think we should be doing, at least in terms of these problems, because a lot of stuff is really happening in chapter 19 and 20, so we really need to get to those two before the spring break. Anyway, so we have problem 68 from this chapter. And it says basically, what is the total random translational kinetic energy of a 5 liter of hydrogen gas? And they give you the molar mass. So we have the volume in this problem, V equals to 5 liters. It's worth remembering that 1,000 liters is a cubic meter. So this volume is 5 times 10 to the negative 3 cubic meter. So if we ever really need to convert, this is what we need, okay? And then so it's the hydrogen gas, and they give you the molar mass for it. That means a mass of 1 mole is 2.016 grams. So the molar mass is equal to 0.16. It's basically 2 protons because it's a gas, an H2 gas, okay? That's what the hydrogen is. Grams per mole. Okay. With the pressure, which is the atmospheric pressure, P being equal 1.01 times 10 to the power 5 Pascal. It looks like we need that conversion after all, because if the pressure is given in Pascal, the volume better be in cubic meter in order to do calculations and have the PV in joules, okay? So we have everything in this case properly. And the temperature, we don't need to convert anything. The temperature is given T to be 300 Kelvin. So we have everything. So use a procedure similar to, I don't know what that problem 1865 is, but it tells you to refer to problem 1865. So obviously I didn't do all of the problems, but hopefully you guys can understand how to tackle this problem. So they want the kinetic, the total translational kinetic energy, okay? Remember, every particle of the hydrogen gas in this case has a kinetic energy which is equal to 3/2 of kBt. This is on an average kinetic energy of every molecule or per molecule. And this is translation because you have 3 degrees of freedom in the X, Y, and Z direction. That's what the 3 is coming from. So this is, if you wish, the average kinetic energy per molecule. Okay, we need all of them. They want everything in this case. They want to know, what is the question again? What is the total random translational kinetic energy? So if we have n of them, that is going to be the total. So the total now, the average kinetic energy, sometimes I write it this way, okay, which is the same, just a symbol in there, okay? Or if you want to, you sometimes can write it as KEAVG. This is the symbol in here, the brackets are simply to denote the average. So in this case, it's just n times this number, times the one that is per molecule. It's worth introducing Avogadro's number, where Avogadro's number is such a way that n over Na is equal to the number of moles. So in this case, N is simply equal to the number of moles times Avogadro's number. So no matter how many moles you have in the gas, multiply it by Avogadro's number. And note also that Na times Kb is just R, okay? That's how Mr. Boltzmann introduced his constant Kb. So in this case, if I do that conversion, so this is simply going to be N times 3/2 of RT, okay? They gave us T, they gave us R. I mean, we know R actually is equal to 8.314 joules per Kelvin per mole. We don't know what the number of moles is, but we know PV equal to nRT, okay? As a matter of fact, they gave us T, they gave us R, they gave us V. V is 5 liters, P is 101 thousand Pascal, and T is 300 Kelvin. So we should be able to find the number of moles, plug it in here, and we would have found actually what this kinetic energy is. So we solve this equation. This gives me P equal to, N is equal to PV over RT. When we plug this N in there, the RT cancels the RT, and it's going to be 3/2 of basically PV. So that's all the answer to it. So the answer in this case is the average kinetic energy for the entire gas is equal to 3/2 of R, 3/2 of PV. That is after we sub the value of the N in there. So the RT cancels. So it's simply going to be P times V, and 3/2. P is 101 times 10 to the power 5. And the volume is 5 liters, or 5 times 10 to the negative 3. And that is simply equal to 101 times 5 times 3 divided by 2. And this is going to be in joules, okay? So because we converted everything. Am I sharing the screen or not? I'm sorry, you need to speak up. This guy's sorry. I'm sorry, I did all of these calculations for nothing. Sorry about that. Anyway, that happened, okay? You need to speak up. I know I saw the note now in the chat, but basically this is the data that is given in the problem. Oh, no problem, okay. It's worth investing in one because the microphones are useful devices. Anyway, so basically in this case, we have the volume given in liters, converted into, and they gave us also the molar mass. In this case, it's this quantity. I don't know why we need it now, but they give us a pressure, they give us a temperature. So this is an indication that if we use PV equal to nRT, we're going to get the number of moles. And we need the number of moles if we want to find the average kinetic energy for the entire gas. So we know it by the chapter 18 that per molecule, it's 3/2 of kBt. Each molecule is bring 3/2 of kBt because it moves in the X and Y and Z direction. So this is the average kinetic energy per molecule, not per mole. I was trying to finish it, but I put the dot in here. So this is per molecule, okay? 3/2 of kBt of hydrogen gas in this case. So the entire kinetic energy, which is sometimes I write it with a bar on top, sometimes I put this average in the brackets in here. Sometimes we use also the symbol AVG. It's just multiply the number of the entire, how many particles you have in there. So we're assuming there is a big N of them, times the average of each molecule. Now gives me, what I did in this case is basically N times Kb is the same thing as the number of moles times R because of the following. The number of moles is just the number of particles divided by Avogadro's number. How many atoms are there, basically expressed in terms of Avogadro's number. That's what the number of moles is. So the number of particles then, the number of molecules of hydrogen in this case turn out to, for those who came in a couple of minutes late, we're doing problem 68, by the way, okay? So we are expressing then this expression in terms of this one. Now we know this is how Kb actually was found. It's just R, the constant that was determined by experiment, divided by Avogadro's number, which was also divided by experiment. So at the end, we have Kb times Na, that is actually R. So if we write this expression now, instead of writing it with the number of particles, the number of hydrogen molecules, we're going to write it in terms of the number of moles. This is how it's going to look like. Instead of Kb, we will have R. Instead of big N, all the particles combined, we will just have the number of moles. The number of moles is just a single number, like 3, 4, 2, 1. So it's a simple number. But the number of particles is of the order of 10 to the power 24, 23, depending on how many moles really we have. If we have exactly 1 mole, it's 6 times 10 to the power 23. Now, KB is actually 10 to the negative 23, because again, KB is just R over NA. So it has that order of 1.38 times 10 to the negative 23. So that is the same expression, either expressed in terms of moles or expressed in terms of the actual particles. The constant changes from being R, the ideal gas constant, to KB, Boltzmann constant, okay? So this is basically just a rewrite of the same expression. Now we have R, and we know also that PV equal to nRT for an ideal gas. We're going to treat this hydrogen gas as an ideal gas, and they tell you to do that. So from here, we find the number of moles, N equals to PV over RT. If we sub that, RT cancels RT, and this is just going to be 3/2 of PV, because N times RT is already included in PV. So then at the end of the day, the expression for the energy is going to be 3/2 times the pressure. Pressure, they tell you specifically in this problem, is 101,000 pascals. Here it is. And the volume, they tell you it's 5 liters. We have to convert it to cubic meter to get the energy in joules, okay? So if we do that, if I pull a calculator, what is my calculator? I need to put a calculator in here, because I don't like to do stuff, especially since we're doing this session. Come on. Okay, so if I plug in the numbers in here, it should give me an energy in joules. So how many energy is that? How much energy is 3 times 101 times 5 divided by 2? Is this believable? 757 joules? That's it? Roughly 758 joules. Doesn't sound much. Anyway, so 757.5, okay? Since we have sig figs everywhere, this is 5.00 actually. This is in known temperature, this is room temperature, and this is the atmospheric pressure. So this is how much joules we have for the entire gas, okay? So that's fine. So that's part A. If the tank containing the gas is placed on a swift jet moving at 300 meters per second, by what percentage is the total kinetic energy of the gas is increased? So there is a plane moving at 300 meters per second, which is, by the way, less than the speed of sound. The speed of sound, if you guys remember, is 343 meters per second. And this is the speed of sound. So this is a subsonic plane, okay? It's not moving faster than the speed of sound. So this is normal. This is typical plane, okay? Moving super fast, jetliner, okay? What is its kinetic energy there? Well, we know the kinetic energy due to the entire gas now is moving with the plane. So it's going to be 1/2 of its mass. Not that of the plane, but on the plane. It's the same gas on the plane. So it's 1/2 of its mass times the velocity squared. Here is the velocity of the plane with which it's drifting. So in this case, I need the mass. I know how many moles we have in here. So we really need this number of moles and times the molar mass, because they give us how much the hydrogen weighs per mole. And it weighs 2.106 grams. Don't forget to convert this one into kilograms if you expect to find this expression in terms of joules. So the mass then of this hydrogen is going to be, hydrogen gas, that is H2, is going to be the molar mass times the number of moles. And the molar mass is 2.016 times 10 to the negative 3, that is converted to kilograms, times N. N, we found it to be PV over RT. So it's PV over RT, and P is 1.01 times 10 to the power 5, that is the pressure, times the volume, which is 5 liters, 5 times 10 to the negative 3, divide the whole thing by R, which is 8.314, times T, which is 300 Kelvin. Okay? So let's do this number in here. So it must be, should not be a big number because of the fact that this is hydrogen after all. It's the lightest gas. So let's do this. So what we have, 2.016 times 10 to the negative, I should have really fixed those powers, but that's fine, times 1.01, 10 to the negative, 10 to the power 5, I'm sorry, times 5, times 10 to the negative. When you're doing problems like this one, you really have to pay attention to your powers, okay? Sometimes that's when you get a lot of mistakes in the calculations. 8.314 times 300 in the denominator. Okay, so man, this is a very small number. So it says 0.4018, now let's write it symbolically. Okay, let's write it in scientific notation. 4.081 or 82 times 10 to the negative 4 kilogram. It's not a lot, okay, because the density of it is too small anyway. So that is as expected. Multiply that by the velocity squared divided by 2. That should give me the kinetic energy due to its motion in the plane. So the kinetic energy in this case on the plane of this same gas while it's moving with 300 meters per second, which is a lot of speed, by the way, is this mass of H2 times 300 squared times the velocity, because they tell us the plane is moving at 300 meters per second, which is a subsonic plane. That means it's moving slower than the speed of sound. Okay, so I'm going to take this mass and I'm going to multiply it by 300 and square the 300 and divide the whole thing by 2. So that should give me 18, that's good, 18.4, roughly 18.4 joules. I expected this number to be a lot less than that of the kinetic energy due to thermal agitation. So thermal agitation is 758 joules, whereas this one is only 18.4 joules. So if you take that gas, because it's agitated, it's moving every which way, it's room temperature, 300 Kelvin. So its kinetic energy on average is 758 joules. So that's the entire gas. Each molecule will have this number divided by Avogadro's number. So each molecule contributes a tiny number, okay? And then it's not exactly by Avogadro's number. You have to divide by the actual n, which is less than Avogadro's number, because this number looks like it's less than Avogadro's number, okay? Or somewhere around there. I didn't do the calculation for n exactly. We need to know how many moles we're talking about. We didn't really need the number of moles because we canceled it everywhere. So again, it's 1.01, 10 to the power. Okay, times 5 divided by RT. RT is 8.314 times 300. Yeah, we're talking 2/10 of a mole, okay? So it's a 2/10 of an Avogadro's number. It's still a big number in here. So to account for the 758 joules of this gas. And then when you take that much gas that is inside a container and you put it on the plane and it moves, this is how much kinetic energy is going to get. It's 1/2 of its mass times the velocity squared of the plane. So that is a tiny fraction of what the total energy is. So it's not really a lot. So what percentage is the total kinetic energy of the gas has increased? So the percentage on average is going to just be the ratio. So the percentage is going to be the kinetic energy when it's on the plane over that due to the thermal agitation. So this is due to the temperature. So it's going to be 18.4 divided by 758, and that should be, by the way, I approximated these numbers, okay? So they're, I'm using in the calculator a more updated version. So in other words, before rounding. So it's giving me 2.4%. Okay, so that is basically what this percentage is. So it changes due to the motion of the plane, which is moving super fast. 300 meters per second is just barely below the speed of sound. But it's still, it does not add a lot to its overall kinetic energy, because at room temperature, the hydrogen gas in this case is moving super fast compared to what it does on the plane. Except that it's going nowhere, because it's going every which way. At the end, it's not traveling anywhere. On average, it's a zero velocity. That is basically what thermal agitation is. If the molecules are located at a distance r2, oh no, what is that? Sorry, I'm reading, no problem. Since the kinetic energy of the gas molecule is greater when it is on the jet, does this mean that its temperature has gone up? No. Obviously, what we're saying in here is that before the plane, it was moving 58 meter per second. When you put it on the plane, on average, it's going to be 788 meter per second plus this 18 meter per second. So that means that the energy overall has gone up by this fraction, okay, which is 2%. This is the total. Does this mean that its temperature has gone up? The answer is absolutely not, because of the fact that 758 in here is due to a random motion. This is not random motion anymore. This is all of the gas is moving in one direction. So when that has actually shifted from the initial value, and the average is still due to thermal agitation 758. So if you're going to take one molecule and another molecule and have random motion in here, and this results in 758 meter per second, which is equivalent to 300 Kelvin temperature, because temperature and average thermal energy are the same. Average kinetic energy due to thermal agitation are the same. So in this case, if you take this gas and shift it now with the velocity every which way, but keep the random motion in, so this shift is not going to change the average. It's going to just change the origin, and the average stays the same. So the temperature stays the same, okay? Temperature is due to a random motion, not organized one. Since the plane now is taking the entire gas and moving it in one direction, case in point now, it does not increase its temperature, okay? The ice will not just melt just because you put it on a car and start moving, unless the car actually gets hotter and hotter. In this case, it's going to warm, okay? So that is really the point in here. So this is problem 68. I really didn't want to spend a lot of time on these problems, but hopefully you guys understand it, okay? I would recommend that you go through this stuff in here again. Problem, okay. I'm gonna mention problems 73 and 76 only, okay? 73, it tells you to find basically the root mean square of the velocity to prove that VRMS is equal to square root of 3 kBT over m. Okay, so for that, they give you an integral in here. They tell you, note the following. The integral tables tell you that if you ever encounter this integral, x to the power 2n, exponential of negative alpha x squared dx, this value is given by 1 times 3 times 5, and so on and so forth, until you reach 2n minus 1. At that point, you stop. You divide that by 2 to the power n plus 1, and you multiply that by alpha to the power n, and then at the end, you multiply it by square root of pi over alpha. So they tell you, basically prove this expression. So in order to do that, all you have to do, you're going to change the expression in here for the average. So what you do in this case is, the VRMS, if you guys remember, is the square root of the average of the velocity squared, okay? And for that, the average of the velocity squared, and they tell you how it's defined, by the way, it's from 0 to infinity in this problem of v squared x times f of v, dv. So what you do in this case, you bring f of v that we defined from lecture, which is this stuff, 4 pi m divided by this stuff to the power 3/2 times v squared times the exponential. So you do that, and you take the square root at the end. So you're going to take the square root of the integral from 0 to infinity. I know it sounds like kind of too complicated, but believe me, it's with just a few change of variables. So it's m over 2 pi kBt to the power 3/2 times v squared times exponential of negative the kinetic energy mv squared over 2 kBt, and another v squared coming from this definition for the average times dv. Okay, and the whole thing under the square root. Now, call m over 2 kBt as alpha, and this will become v squared and v squared, that's v to the power 4, so it's already n is equal to 2. And you apply the formula after you call this alpha, this is constant, okay? So all of this stuff will come out of the integral. And you do the algebra, and you're going to get this result. Okay? You're going to get exactly that result. The same thing with problem 76. So I'm not going to do that because it's really just a change of variable. So call this quantity alpha, plug it in here, and note the following, that n is equal to 2 then, because you have v squared, v to the power 4, and the expression that you need is x to the power 2n. So if you want this number to be 4, that means n is equal to 2. So n is equal to 2. So when you apply this formula, actually you stop at 3, because 2 times 2, that's 4 minus 1, that's 3. So it's 1 times 3 divided by 2 to the power 2 plus 1, that is 2 cubed, times alpha, which is this number, to the power n, which is squared. Okay? Times square root of pi over alpha at the end. So you use that to find the answer for yourself, and you're going to get exactly square root of 3 kBt. Because at the end, it's going to be kBt that is left times 3 that is going to survive this whole thing. Problem 76 is similar. Again, if you're familiar with the Gaussian integral, this is useful. If you're not, just use the table of integrals. You don't really have to prove this expression. It's already given to you. And that is identical also with problem 76. For problem 76, they tell you, you want to find now, instead of that, you want to find the average of v f of v, okay, dv. So this is the actual average of the velocity. So this is the v mean. So for that, you're going, no square root at this point, okay? So what you do in this case, you're going to take the entire expression and you have v cubed in here, times exponential of minus something v squared in here, okay? Now, what they tell you, what you need to do now is you need to do 2 change of variables, because you will have, let me write this expression first, okay? So it's going to be 4 pi times m over 2 pi kBt to the power 3/2 times v squared, and v, that's v cubed actually, times exponential of minus mv squared over 2 kBt times dt. I'm sorry, dv. So this is the expression. So the integral, I'm sorry, from 0 to infinity, the integral from 0 to infinity. So when you do that, you note the following. When you do the variable, first of all, you're going to call the variable x to be v squared. That immediately will give you dx, I'm sorry, equals to 2v dv. So one of these v's dv's is going to be dx divided by 2. The other v, which is v squared, is just going to be part of the definition now, that is going to be x. So you're going to end up with an integral. Of course, you define also alpha in the same fashion as you defined it before. Alpha is going to be just m over 2 kBt. Okay? So this is going to be exponential of minus alpha x, because v squared itself is x, and this whole thing is just alpha. So it's going to be exponential of minus alpha x, and now v dv is just dx over 2. So this is divided by 2 times dx. Remember, I took one of the v's now in here from the v cubed. v dv is already dx divided by 2, and I'm left with a v squared. V squared is exactly x by my definition. So this is the integral that I'm going to do, plus the rest of the stuff, which is just constant. I'm not writing it in here. So the integral in here is going to be from 0 to infinity, plus the other stuff that I'm not writing. So at the end, and the 2 actually becomes part of the other stuff that is also out there. So we're going to have the integral with n equals to 1. And if you do that, the answer should be this part of the integral only, okay? This integral only becomes 1 factorial, which is 1, over alpha to the power n plus 1, which is 1 plus 1, alpha squared. So you apply that, you don't really have to do this integral. It's already done for you. And you get the answer, and you multiply it by the rest of the stuff, and you're going to find the average velocity. Okay, so this is some of the stuff that we found last time, but we didn't do. So this is problems 73 and 76 at the same time. Okay, so I'm not going to carry the calculations because it's just manipulation of these constants and moving things around without actually having to do the integrals because they were given to you. Now, the last problem that I'm going to discuss now is problem 78. So problem 78 is actually a bunch of data. They tell you a steel cylinder with rigid walls is evacuated to a high degree of vacuum. You then put a small amount of helium into the cylinder. So we have helium, He. Okay, there was a question in here already about this problem. What is the problem? The first problem, because we use hydrogen. For hydrogen, we use 3 halves in here. And remember when I was making a big fuss last time in lecture about the CV, no, chapter 18. Why did we do this in here? We have two chapter 18 problems. Anyway, so I started this one and then I moved it in here. I'm sorry about that. So I probably have to fix that. Anyway, so when we did chapter 18, actually, here is the discussion that I was referring to in here. When we calculated CV, if you guys remember, CV turned out to have 3 halves of an R for a monoatomic gas, and for a diatomic gas, it's 5 halves of an R. And this problem, hydrogen, is actually a diatomic gas. But I'm not trying to find the change in the energy of the system. I'm trying to find the kinetic energy only due to translation. So when you do the kinetic energy of translation for anybody, it doesn't matter, polyatomic, diatomic, monoatomic, it's always 3 halves, because in translation, you can move along the x-axis, the y-axis, and the z-axis only. So we're not considering the rotation in here because we want to compare apples to apples. The rotation in the translation in this case has 3 halves no matter what. Even though this gas is H2, it's diatomic gas, the kinetic energy still, due to translation, 3 halves. The problem was specific to look at translation. So to compare it with the fact that we put that gas now on a plane, which is also another translation. So we're comparing translation to translation due to the random motion of the thermal agitation compared to that when it's on a plane. So this is a big distinction. Please do not get confused with it, because in the later on, especially with chapter 19, we will make this distinction big time between, for example, a helium, which is a monoatomic gas, where CV there is clearly equal to 3 halves of an R, versus a diatomic gas, like an H2 in this case, which is 5 halves of an R for CV. But we're not concerned with CV. We're concerned in the translation in the previous problem. That's why we use 3 halves, okay? These guys don't have translation. They have only pure, they don't have pure rotation. They have only pure translation. The monoatomic gases like helium has only pure translation. It's a point. It does not spin on anything. It just moves in, out, up and down. That's it. So this problem now deals with that, except that it doesn't deal with the question in hand. But just to answer the question, if you guys are confused, why did I use the 3 halves in there? Because we were just concerned with the translation, even in that problem with the diatomic gas. So steel cylinder with rigid walls is evacuated to a high degree of vacuum. You then put a small amount of helium into the cylinder. The cylinder has a pressure gauge that measures the pressure of the gas inside the cylinder. You place the cylinder in various temperature environments, wait for the thermal equilibrium to be established, and measure the pressure of the gas. So what we have in this case, we have the pressure in Pascal. And we have the temperature in degrees Celsius. It is very important to remember that this temperature in degrees Celsius, so we better change it to Kelvin. Okay, if we're going to draw PV equal to nRT in here. The volume is fixed. The volume is constant. And they gave a different temperature in here. Negative and negative 195.8, 0. So this pressure in here was 254 Pascal. Now it's 890 Pascals. And 333.3 degrees Celsius. So it's 999, almost 1,000. Then for 100 degrees Celsius, it's 1,214 Pascal. And finally, it's 232 So this is still helium, okay? So this is not the air, so that you're worried about that, okay? So 1,635. So again, recall chapter 17 that absolute zero is a temperature at which the pressure of an ideal gas is zero. So use the data on the calculated to get the absolute 0 degrees Celsius, to get the absolute 0 in degrees Celsius. Okay, so you take this data, you convert it to Kelvin, or actually leave it in degrees Celsius. That's fine. Okay, so this is how you're going to plot this function for the temperature in degrees Celsius and the pressure in Pascal, okay? When it's negative 195, it's somewhere in here. The pressure is 254. Let's say, for example, this is the pressure. For 0, it's 890, which is about, what, 4 times this number or something? It's almost 4 times this number. It's in here, okay? And then for 33 degrees, which is immediately, there is a big gap between 195 and this one. So it's probably somewhere in here. And then for 100 degrees, which is slightly almost halfway in here, it's 1,200, it's somewhere in here, okay? And then for 232, which is almost slightly more than this distance in here, it's increased to about 1,600. You plot these numbers, you're gonna get a line that looks like this, more or less, okay? So we're going to get a function P as a function of temperature. It's going to be a linear line that is m times T plus P naught. Okay? P naught is going to be the y-intercept in here. Okay? So this is going to be, P naught is going to be exactly 890. Because for temperature equals to 0, that is 890. Now we're going to find the y-intercept, the x-intercept by equating this equation to 0. So when the pressure is 0, that means the temperature should be minus 890 divided by the slope, okay? So the slope, you're going to get it from Excel. This number should be comparable to 273 number. In other words, this number should be around negative 273 point something, okay? Compare that to the actual value, which is 273.15 with a negative sign. So that is your absolute Kelvin. That is the temperature where the pressure is supposed to be 0, okay? Then use the, what is this one? Use the coefficient of the volume expansion for steel to calculate, because we considered the container not to change in volume, but it does, okay? So there is a change, there is an error in there, that is, you're going to find it. And based on that, you're going to basically, because you can use delta V over V naught, which is going to be simply equal to 3 alpha times delta T, okay? So this is basically the alpha of the steel. And this expression, we proved it in the class, actually in the lab, that it's, because this is a volume now. So the volume changes by this much. So this is the percentage change in the volume. So use the alpha of steel, which is a very small number, times the change in variable. Change in temperature from the lowest to the highest, they tell you. So you're going to have 232 minus 195. So it's going to be 234 plus 195, which would be about what? 400 and something. And that is the same thing in Kelvin, the same thing in, because you're taking the difference. So the difference is going to be in Kelvin, which is fine, times alpha, the coefficient of linear expansion, times 3, because it's a volume. So at the end, you're going to find the error you made in making that assumption, in making the assumption that the volume does not change. But you know, and I know that the volume will change, okay? So based on that, you're going to estimate the error. This is how much error actually you measured your absolute temperature, okay? So this error that you have made is making the assumption that the volume does not change, but it does, because you use the expression PV equal to nRT to plot this function. PV equal to nRT to plot this function, where V you assume to be constant. So P is supposed to be an ideal gas law, where the volume does not change. If you keep the volume constant, the temperature and the pressure will be a linear function, but it is not. This expression, of course, is written in Kelvin. So if you really want to write it in degrees Celsius, so if the temperature is measured in degrees Celsius, you have to add to it 273. So that is basically what the error is coming. So the error that you measured, which is the entire graph now written in degrees Celsius, this is basically where your error is measuring this value. That's what you really want to do. In measuring this value, you made a mistake in making the assumption for V, assuming that when you measure the temperature, the thermometer was properly gauged, and also the temperature measurement was also gauged properly. So the error then is in assuming that the volume does not change. This is how much error you made into this calculation. Does this problem make sense to you guys? Yes? Okay, very good. So we're done with these problems. I did not really want to spend a lot of time, honestly, and it seems I did, on these problems. But I'm hoping that they clarify some of the concepts that you need for this class anyway. So it's really not a waste. Let's get into chapter 19, okay? The first thing I'm going to start with is the first law of thermodynamics. I have a gas in here, and I have a, let me redraw, it's no good. If I have a container in here, and on top of the container, I have a piston that can or cannot move. I have two options for it. So this is a piston, okay? So it's fixed from the other sides and only allowed to move in one direction and one direction only, okay? Which is this direction, the y direction, if you like to call it the y direction. This piston has cross-section A, obviously, okay? So in this case, if I come and fix these sides, the piston, put it in place so that it doesn't move. Then in this case, the piston, the entire gas that is contained in here, which is properly sealed, of course, the volume does not change. So if I put in here this entire thing under, for example, a heat source, then in this case, the temperature starts to change because of the increase in here of heat that is coming to the gas. If I put a thermometer in here, it's going to give me T going up. As a matter of fact, the pressure also goes up by PV equal to nRT. So I know that the temperature is going up because, and the pressure is going up because I'm adding heat to the system. So one way for me to basically add heat in the gas, in this case, is by simply adding heat to it. That's it. So that is going to raise the temperature, which means that, if you guys remember from the previous discussion, that the internal energy of the gas will increase, because remember how much this will increase. It's NCV delta T. So if delta T changes, then the internal energy of the gas increases. Okay, so that's one way for me to increase the energy of the gas. Another way of doing it is the following. Taking the gas in here. So in this case, there is no change in V. V is constant. Okay, does not change. Another way for me to do the same thing is the following. Taking a gas, for example, and now not fix the piston. Leave the piston now not fixed. Take again the thermometer in here, read the temperature, the gauge, and everything else, and also now the volume is changing. So what I do in this case, take the piston, which is properly sealed, by the way, okay? It has a cross-section A, by the way, and move it down with a force F. So if I move it a distance dy, obviously the volume went down. Do you guys understand? Does it make sense? That if I move the piston on the gas, the volume shrinks by ADV, ADY. So dV in this case is going to be ADY. It's less volume. This is the amount of shrinking of the gas. It compresses a little. Yes? Makes sense, doesn't it? This is how much volume changes, because the piston has a fixed cross section A. So if I move it a distance dy, the volume of the gas shrinks by this much. Correct? Area times the height. So if it was V naught in the beginning, now it's V naught minus this number, actually. Does this make sense? Okay, very good. So that's basically how much change in the volume of the gas while I'm doing that. Obviously, I'm pushing this way with the force F, okay? And this corresponds to an amount of work from my part. So this is how much work I need to do. It's force times displacement, okay? And this force times displacement, if you guys remember, the pressure is force over area. So that means that the force is simply pressure times area. So that means that the amount of force I'm doing, actually, I need to do on the gas is P times the area times dy. So it's P dV. That's how much work I really have to do on the gas. Okay? Make sense? In magnitude only. Makes sense. Very good. So here is the deal. From the vantage point of the gas, the pressure is actually pointing this way. This is the pressure. Okay? The pressure is going up. Okay? So I really have to fight that pressure of the gas in order to do this work. So from the vantage point of the gas, this is basically just a minus, because the pressure is pointing up, namely the force that the gas has to exert is going up, and the displacement is down. So the work in this case should be minus P dV, that's all. This is by the gas. In other words, I have to do really that much work for me to do it. So what's going on in this case? Where did that work go in terms of the gas? It must have gone to increase also the energy of the gas. If I do work on the gas, if I compress the gas, I actually change its internal energy. If I assume that somehow the gas is insulated in here, there is no heat in or out, it does not lose heat in the process, I expect this gas internal energy to increase, which means that also that results in the same effect, that delta U will increase. If compressed, the internal energy of the gas increases, because it has to go somewhere, because I'm the one who's doing the work. It's the outside that is doing the work on the gas by compressing it. So that is have to go somewhere, and it goes to the internal energy of the gas, especially since I'm isolating it now and wrapping it in a big blanket so that it does not lose heat or gain heat for that matter. So in this case, the only way for the energy that I am putting in to go, it's going to go into the gas, into its internal place. Okay, so that is another way for me to increase the energy of the gas. Now, if the gas expands somehow, okay, if the gas expands, then it's going to lose energy because it's going to do work against the environment. Then it's going to have to come up with that energy somehow. And the only place that it has energy is only internal energy. So this is if we compress it, but if the gas expands, if the gas expands, it must do work against its environment, resulting in losses of internal energy. So that is basically in a nutshell what's going on in here. When it does work, its volume expands. So dV will become positive. If dV is going to be positive, it's going to lose energy. If dV is positive, it's going to lose energy. So this is basically what's going on. If dV is positive, then du must be negative. Then it must lose energy. If dV is negative, when I compress it, I'm adding energy to it. So that's where the minus sign is needed in here from the vantage point of the gas. This is unlike the book, okay? I'm going completely against the convention in this book because this is actually the universal convention that I'm using, okay? This is what you will find in almost every other book, okay? That the energy in this case, the change in the energy of a gas, this is the first law, by the way, is equal to the heat added plus the work that is done against the gas. So this is basically, in a nutshell, the entire expression. This is the first law. This is the first item of discussion, by the way. First law of thermodynamics. Two-way thermodynamics. Two ways of increasing the energy of a gas. Either by adding heat or doing work against the gas, compressing it. I mean, if you did not really add heat to the gas, but rather you extracted heat from it, then the energy will go down. If you take it and put it in a refrigerator, for example, and start removing heat from it continuously, then its internal energy will go down. Case in point, take a thermometer, read it before you put it in the refrigerator, you'll find it higher than when you pull it out of the refrigerator. So its internal energy went down, actually. Or by having it expand and do work against the gas, the environment. This is exactly what's going on when you have a pressure cooker, for example, and you poke a hole in it or you remove that cover. So what's going on in this case is it has a lot of internal energy inside. It has a very high temperature actually that goes with it. So when it comes out, it's going to expand in the outside. And if you put your hand, don't do it. It's super hot, okay? Closer put the thermometer instead. Closer to the hole is going to be very high temperature versus when it expand, okay? Then it's going to be at room temperature. So that is actually, it lost energy in that case by doing this expansion. It's going to move against the environment in this case. So those are the only ways. So this expression actually talks about how do you change the energy of a gas by either adding heat to it, quote unquote, removing heat from it will result in removing energy from the system, having delta U negative in that case, or having the gas being compressed, in this case also will raise its temperature, will raise its internal energy, or in this case, quote unquote, between parentheses, also having the gas do work, in this case is going to lose energy. Does this make sense? This is your item of discussion. I want you to put it in your own words. Okay. So this quantity is algebraic values, by the way, meaning that they can be positive or negative. Your book uses the symbol negative in here because it defined the work completely nonsense, okay? Work is actually defined as minus the integral of PdV from initial to final, okay? And the minus now is natural, meaning that is dV is negative, minus negative, that's going to be positive, so that means the work is going to be positive. That means actually the gas is going to do work against I'm sorry, if dV is negative, that means I'm compressing it, I'm making it smaller and smaller. So if I multiply it by negative, that's going to be a positive. So that means work is going to be a positive value that you're going to add it to the delta U. That means you're increasing the energy, because as you make the volume less and less, multiplied by negative, it's going to be a positive value. You multiply it by P in this case, and now all of a sudden you have increased in the energy of the system. If dV, on the other hand, is positive, that means the gas is expanding. If dV is a positive, that means the gas has increased in volume. If dV is positive, its negative is going to be negative, then in this case, it's going to be loss in energy. So it's natural to explain it this way with a loss and gain. Then having to define work somehow against the wisdom from the vantage point of the external environment. This is how the book defines work, by the way, from 1 to 2, PDV, and the expression will not change, will be the same. So if we do it this way or the other way, the book, of course, will then gets into the first law as being delta U is equal to Q minus W. And again, this, if I plug the value that the book has defined this way, or the way that is defined in everywhere else, is going to result in the same result. So if you define the work and you're going to do the homework problems following this convention, and you may have to do that, and if you run into some problems with the online homework, please let me know. Then, so that to override it, because I'm telling you this is definition that is not conventional, by the way. So if you find that you plugged in the minus and the homework online is not giving you the correct answer, let me know and I will override it, okay? Because it's very important that we have to have a clear concept, idea in there. Then delta U, if you do it this way, like the book is doing it, it's going to be Q minus W. It's going to result in the same value of the energy, end of the story, okay? The interpretations are completely different, but in this case, it's really natural. So this is how you're going to be doing it. I hope that this clarifies this issue with the first law. Make sense? Okay, very good. So please, if you have any confusion about this one or you have issues with it, please let me know, because I'm trying to give you the universal definition for it. This is what every textbook out there and literature talk about it, and it's actually nicer this way. It's much more symmetrical this way. When you see a plus in here, just like when you were doing with the mechanical energy as being the potential plus kinetic, this is similar in that fashion, except this is the internal energy of a gas, and this is the first law of thermodynamics, okay? So let's do some processes. Let's talk about, so this is basically a common thing that is going to take us for the rest of this, basically 2 chapters. So what we're going to do is imagine that we have a gas sitting at specific volume and pressure. So it's at equilibrium at this point. So in this point, it has a volume, which I'm going to call V naught, and it has a pressure, which I'm going to call P naught. So in this case, exactly I know, so in this point is defined with the coordinates V naught, P naught. This is the PV diagram, by the way. In the PV diagram, every point on this space is defined with a coordinates with volume and pressure, okay? As opposed to a TV diagram where the coordinates are temperature and pressure, temperature and volume, or a TP diagram where again, temperature and pressure. So this is a PV diagram, which is I think 99% of the problems in this class are going to be a PV diagram, and this is actually the most universal used, at least in terms of education. I know in engineering, there are special applications where you don't really use PV diagram, you use other diagram, the mechanical engineer and some heat flows and things like that. Anyway, now at this point, the temperature is well defined because again, this is an ideal gas. So we know at that temperature, at that point, it's NR naught, T naught, PV naught. So we know the temperature. So this point has specific values in it. So if we know its volume, we know its pressure, we know its temperature. Since we know its temperature, theoretically, we know its energy. We don't care what its value is because most of the time we care only about the change in variable, in temperature, in energy, I'm sorry. So these are called state variables. Meaning at this point, which is the state of the gas, we know all of these values. They're given, they're known, or they can be calculated basically, okay? On a point where the temperature doesn't change, if the temperature is fixed, constant, I can graph the function PV equal to a constant nR T naught, where T naught doesn't change, constant. So if the temperature doesn't change, the pressure is just 1 over X in this case. So the pressure is going to just depend like this. So this is a curve whose temperature does not change at all. So the temperature in here is the same. Obviously, if I go to another point on the PV diagram, this will have another volume, V1, for example, and another pressure, P1, for example, and the temperature is the same. Okay, the temperature is the same. So this is called an isothermal. So an isothermal is characterized by the same temperature. So an isothermal has the same temperature everywhere on it. Since it has the same temperature, also has the same energy, by the way, because temperature and energy are measured of the same thing. So if it's the same temperature, the energy is the same. Okay. In other words, if I go from this point 1, point 0, actually I labeled it 0, to point 1 on this isothermal, there is no change in the energy. Actually, delta U is exactly equal to 0. Okay, and that is an important result. So on an isothermal process, like this one is called an isothermal process. Delta U is equal to 0 because T is the same. That is what an isothermal is. Temperature doesn't change. So if temperature doesn't change, there is no change in the energy of the system. It stays the same. So as a matter of fact, more than that, because the change in energy is equal to Q plus W, Q and W are opposite to one another. Q is just equal to minus W. That's it. Okay. So whatever heat you add to the system is going to basically be done by expanding the gas. Because the gas went from volume V0 to a volume V1, this is actually thermal expansion, isothermal expansion, to be more specific. So this example, in the one I drew in here, if I go from point 0 to point 1 in this direction, I am actually going on an isothermal expansion. Isothermal expansion. Here is what's going on. The gas takes heat from the heat source, from this, the reservoir of heat that is fixed, that does not, temperature doesn't change. So this is actually, since the temperature doesn't change, it becomes a reservoir of heat. Reservoir of heat, because the gas can take heat from it at will. It took already heat from it, but to maintain delta U equal to 0, okay? And the temperature doesn't change. So it's a reservoir. It's like, for example, a big ocean. You go and take a bucket from a big ocean, it's not going to change. You're not going to change the amount of water in the ocean just by taking, for example, a cup of water. It's not going to change. Okay, or even a swimming pool, if you take a cup of water from it, it's not going to change. So this is what we call a reservoir, the word which is really stands for like a big tank of, okay? So you have a big, huge tank of heat that you're taking from it, heat in this case. And as you take heat, the gas is actually expanding. And as it expands, so it takes heat, so its energy is supposed to increase, but it expands, it does work of that heat. So at the end, the amount of heat it takes algebraically is equal to the amount of work it does. And they're equal to negative one another because the temperature doesn't change and the temperature and the energy are the same. So this is an isothermal process. This is process number 1. We need to keep track of these processes. Okay. Here is another way of looking at this. Another process actually of interest. Obviously, there is another way of doing this. Actually, I just didn't mention it, but it's important. So it's expanding. Okay, so when it expands, it does work. So the work is going to be this way. The work actually is this area. If you guys remember, it's the integral of negative PdV. So it's actually this area. And this is exactly how much heat is in there. So if you want to find exactly how much work is in there, let's find it, because we didn't really calculate that work. Let's find this integral, okay? Remember, the work is equal to, I'm going from V0 to V1 of P dV. And I know that P is equal to nR T0, temperature doesn't change at all in this process, divided by V. So if I plug in that expression, I will find the integral, negative the integral from V0 to V1 of nR T0 times dV over V. and nRT naught are constant. The number of moles, they are, and the temperature in this process doesn't change. So in this case, the work is going to simply be equal to minus the integral from V naught to V1 times nRT naught of dV over V. And what is the integral of dx over x? If you remember from your calc classes. What is the entire derivative of dx over x? Do you guys remember? Come on, guys. You can just guess. Did you do this integral already in calc or not yet? Yes? No? Yes? Okay, do you remember it or not? Yes or no? Isn't that the natural log of x? Plus constants, of course. Does this ring a bell? Okay, very good. So this is actually the natural log. Since this is a definite integral between V naught and V1, so I'm just going to ignore the constant because the constant is going to be just, this is for an indefinite integral. This is actually a bounded integral. So it's going to be minus nRT naught, the ln of V1 minus the ln of V naught. And this is ln of A minus ln of B is just the ln of the ratio, because this has a negative, so it's going to be just minus nRT naught ln of V1 over V naught. So this is the amount of work really needed in this case, okay? So it's a very important result that you have to remember. The final volume over the initial volume, you take their log, the ln, the natural log, not the log in the base 10, and you multiply by nRT naught. That is going to be exactly the work in this case. Since it's an expansion, V1 is greater than V naught, so this ratio is more than 1, the natural log is more than 0, and this whole number is negative as expected because the gas went through an expansion, so it must have lost energy during the expansion because in the form of work. But in the same time, it must have gained the same amount of heat. To do that, Q is equal to positive nRT naught ln of V1 over V naught. To do, so that if I add these two numbers, I'm going to find delta U equal to 0. And this is again because I'm doing an isothermal expansion. Delta U doesn't change in this process. So this is the integral, the one that I just calculated, the integral in this fashion here. Because I'm going, and this is exactly why I'm being picky on this convention of science. I'm going clockwise. I'm going from from V naught to 1, back in here, down, back in here, and then back in here. We're going actually clockwise in this integral. We expect it to be negative because we have a convention about the signs that if you go clockwise in any curve or angles, it's going to be negative, and that is expected, and it is. It is negative. Unlike this convention somehow that you have to do it this way, it's going to be positive, doesn't make sense. But you're doing the integral here from the beginning to the end, the integral is going to be negative nicely as it should be, okay? And the work is negative because you're losing energy in the form when the gas is actually expanding. And it's gaining heat to do that. It's taking heat from this source in here, from the reservoir in such a way that at the end of the day, it's going to have no change in energy because we want it to have no change in energy, okay? Because of the fact that this temperature doesn't change. We are on isothermal. Does this make sense to you so far, this process? Because we have 3 more processes. We have the process that is known where the volume does not change, in which case it's a very easy calculation. And we have the process where it's called an isochoric process, And then we have the isobaric process where the pressure doesn't change. And then we have the process where the actual heat there is no exchange of heat, okay? By the way, and I didn't mention that when I made the case about the state variables, Q and W are not state variables. There is no way to say that the gas has a work while at 0.0 or while at 0.1. But in going from 0.0 to 0.1, it did work. It did do work. If I compress it, if I go in the opposite direction, I'll have to do work for it to compress it from V1 to V0, okay? So in that case, I have to do work. So work is not a state variable. Q also is not a state variable. I cannot say since has this temperature, it has heat. That doesn't make sense. When it goes through an expansion like this one, I have to add heat for it to expand. When I compress it, actually, in this case, I'm removing heat and dumping the heat through an exhaust system of some sort outside, okay? That is exactly what's going on in the refrigerator. Behind it, there is heat that is coming from the food that you're removing the heat from it, okay? So this is basically process number one. Process number two that I wanted to talk about, because it's kind of nice too. And process number two is the isovolumetric, I call it isochoric because it's easy, meaning that there is no change in volume. Since dV is equal to 0 in this process, it's very easy. dV is equal to 0. That means W is equal to 0. Remember, W is the integral from state 1 or initial to final of PdV. And if this doesn't change, then this whole thing is 0. So that's an easy process. Let's see how it looks like on a PV diagram. I'm going to take a gas. As again, this is the volume. This is the pressure. And I'm going to take a starting point in here. That is V0. An ending point in here. I mean, starting point P0, V0, P0. But I'm going to go on this line so that the final volume is P1, but the volume pressure is P1, so it has gone in pressure. Actually, I'm going in this direction. So the pressure went up. Actually, this sits on an isothermal, which I'm going to call T1, and this sits on another isothermal called T0. So the temperature definitely went up from T0 to T1. So there is an increase. So this point in here has coordinates V0, P0, and this coordinates has V0, P1. So if I want to find the temperature in here, the temperature T1 is equal to P1 V0 divided by NR. So the temperature now, because the pressure is higher, the temperature is higher, then this point in here, which was T0, is equal to P0 V0 over NR. Okay, since the volume is the same and the pressure is less in here, so the temperature T0 is less. So there is definitely change in the energy, and the energy in this case is U1, and the energy in this case is U0. So the energy went up because the temperature went up. So there is a change in the energy, so delta U is not equal to 0 actually in this case at all. So this is called an isochoric process or isovolumetric process where the volume does not change. Okay, so W is 0. So every time you see an isochoric process, you know W is 0. That's easy because volume does not change. So in this case, delta U is simply Q. Okay, that's it. Plus 0 if you like. So it's Q. And delta U is equal to NCV delta T. So in this case, Q is simply equal to N times CV times T final, which in my case, I wrote the T1 and T initial. So that's the only thing in here. So that is how much actually delta U, that's how much the energy has changed. And that's how much heat was added to the system. So you have to heat it up from T0 to T1. So you have to dump heat to the gas in this case. And the volume does not change. This is the first process that we talked about when you seal the piston. So you seal the piston, you fix it in place, and then you start adding heat to it. So this is how much change in the energy is happening in this case. So you add heat to the gas, end of the story. And when you add heat to the gas, the temperature changes, and the change in the energy is positive in this case, because I'm assuming that T1 is greater than T0. If I go in the opposite direction, if I go from this pressure P1 to P0 at constant volume, then obviously the final temperature will be less than the initial temperature. In this case, I'm extracting heat from the gas, that's all. I'm cooling it down, okay? So that's it, I'm removing heat from it. I'm putting it in contact with another source that removes heat from it. Put a lot of ice, basically. Take the whole gas, seal it properly so that its volume does not change, this case, and dump it in a big bucket of ice, okay? Make sure that it loses heat and the volume does not change. So if that's the case, then in this case, its internal energy starts to change. And if I wait for the equilibrium, it's going to, again, get into this same thing in here. Both of them, T0 and T1 in this case, are isothermals, meaning that they are connected to some sort of a heat reservoir still. So there is a heat sink that is sitting at T0 and another heat sink sitting at T1, and both of them are different temperatures. So if I do the ice bucket, make sure that the ice, you have a lot of it. So no matter how much heat you remove from your gas, the ice does not melt, does not go through a phase transformation. So it stays at the same temperature, basically, okay? So that is to do this experiment properly. Does these two processes make sense? Yes? Okay, very good. So the last process I'm going to explore today, I'm going to leave the adiabatic process for next time when we meet, is the process number 3, is the isobaric process. Okay? Isobaric process. Again, I'm going to take a PV diagram. In the PV diagram, my starting point in here has a V0 and P0. And my ending point in here, again, has the same pressure, but a different volume. So I'm going to go from this temperature, which is T0, up to this temperature. Again, this is clearly an increase in temperature in here, T1. So this point in here is P0 V0 equals to nRT0. And in this case is P0 V1 is equal to nRT1. Obviously, since the volume went up in this case, it's clearly that there is a change in. I'm going this way. So it's an expansion also at constant pressure. So the pressure is the same. So delta P is equal to 0. So the pressure does not change. So this is what isobaric stands for, okay? So I want to find now the change in the energy. Obviously, I'm doing work in this case. Going from V0 to V1. So W is minus the starting point, start, to finish, of PdV with a minus sign in it. P is the same, it's P0. So it's going to come out of the integral minus P0 of the integral of dV, which is just V final minus V initial, which is V1 minus V2, minus V initial. So this is the work, which is kind of easy because you don't have to worry about that ln or anything like that, because the pressure is the same, does not change. Now Q needs to be defined. How much heat is added to the system? We're going to come up with something else. Okay, we're going to define specific heat at molar specific heat at constant pressure. In such a way that this is equal to NCP delta T. So in other words, CP, which is what I'm defining in here, as we defined last time, CV, which is molar specific heat at constant volume, this is the same thing, but it's at constant pressure. So every gas will have its own CP, and we're going to find what that CP is. I know for CV, the monoatomic gas is 3/2 of an R, the diatomic gas is 5/2 of an R, and the polyatomic gas behaves more like 7/2 of an R. We need to find the CP also in a similar fashion, okay? So we need to express it, as a matter of fact, in terms of R2. So at this point, we're going by definition. So in this case, it's going to, if I know what CP is, it's going to be just T1 minus T0, okay? So in such a way, then, in this case, I can find the change in the energy. Obviously, in this case, there is both Q and W, okay? I cannot say that, hey, there is delta U is 0. No, the temperature has changed. I cannot say that that W is 0 because the volume has changed. As a matter of fact, W is going to be negative value because I'm expanding. The gas is expanding. I cannot say that there is no exchange of heat in this case because there is definitely temperature has changed in this case. Not only that, but the work in a fashion that is not necessarily the same. So in this process, this is a process that involves all three of them. So here is, by definition of CP, which we're going to find it. So the question is, what is CP? And that we're going to leave it for next week. Okay. So we need to find what CP is. And then we're going to do the rest of the, so we need to answer this question because we basically defined it in terms of the heat that is added at constant pressure. By definition, just a change in temperature times that value, whatever that is. And since it's molar, it's per mole, that is. So the number of moles needs to be put in here. So N is natural in here. N is by definition, because we decided that this is a molar. That means it's for 1 mole, okay? So that is fine. Delta T is because we want to say, okay, we have a constant pressure, but the gas temperature has increased. So I'm going to have a definition for a value that is going to keep track of that. And that is where the molar specific heat comes into play. So basically we put it in there. And we're going to find this value next time when we meet. So that's the first part. And then once we do it, then we're done because this is done. You have NCP T1 minus T0. Obviously, if I go in the opposite direction, if I'm compressing the gas in this case, this will be a negative value because the final temperature will be less than the initial temperature. And this will be a positive value because then I'm compressing the gas. And this value will, whatever it is going to end up, there is a change in the energy end of the story in this case, okay? So we're going to find a value in there. So I'm going to finish this calculation on Monday. And then we introduce a fourth process called the adiabatic process, which is part of our lab, actually. And then we're done with this chapter, okay? Then we're going to introduce the second law and do some problems, a lot of problems from this one. Good? So many ideas introduced today. I know chapter 19 is kind of heavy. Okay, very good. So hopefully focus on this stuff in here, and we're going to meet on, some of you were meeting in the other classes of Physics 4B. So I'll see you, and then others will talk about this one Monday. Okay, hopefully the recording will be available for you guys. Let me stop the recording in here.